So as I told you, the first similarity is that the halogens also need one electron to complete their octet, or you can say to attain stability. So similarly, the hydrogen also need an electron to complete its duplet, right? So as I am showing you with an example, we have fluorine, we have, so first of all I am writing the configuration for it, that is 27, 287, right. So somehow all the elements has got the 7 as valence electron, right. So I am just showing you that means it has 2 7, that means it needs 1 electron to complete its octet, and after this thing gaining 1 electron, it is just forming the electronegative ion, and the electronegative ion has electronic configuration as 2 8, that means the octet is complete and it becomes a stable ion, right. But and similarly when we talk about the in case of hydrogen, so hydrogen has got 1 atomic number, 1 electron, so that means to attain stability it needs 1 electron, because electronic configuration is also 1, right. So it means it has 1 electron in its valence shell, and we know that if the valence shell is the first shell, so it at least it has the 2 electrons. So that means it can gain 1 electron, forming an electronegative ion. So that means after gaining 1 electron they are attaining stability, the halogens, and similarly the hydrogen after gaining 1 electron is attaining the stability. So that means it shows that they are just linked with each other, right. And the second property which is striking, the second similarity you can say that is striking in my mind, is that it is an electronegative element, or you can say it is forming an electronegative ion. I have shown with the examples, see they are gaining electrons and they are just acquiring the negative charge. It is also gaining electron and acquiring the negative charge. So that means what kind of ion it is forming? It is forming the electronegative ion, like the halogens form the electronegative ion, right. So that means it has been justified, the second property is done as well. So the third property which is striking in my mind is that their atomicity. Now what is the atomicity? Atomicity means the number or the types of atoms which are present in a molecule. So if we look for the, you can say the molecule of the halogens, or if we look for the existence of the halogens, that how they exist in nature at room temperature and how the hydrogen exists, so we get to know that both exist, like the chlorine, fluorine, they all exist as gases, that is Cl2, and similarly the hydrogen exists as H2. We know that, you know that I have told you in bonding as well, that how the bond is formed between them. It has got 7 electrons, again it has 7 electrons, so I have just shown it. This is an electron cloud, so they are just sharing an electrons. That means the 2 chlorine atoms are just joined by a covalent bond, forming the chlorine molecule. Similarly the hydrogen too, the hydrogen and the hydrogen, they have 1 electron. To complete octet, they are just mutual sharing their electrons, and they result in the formation of one single bond, that is again the covalent molecule, and this thing, the atomicity is going to be H2. So that means that it is also diatomic like the halogens are. So that means I've just told you that there are so many similarities that they possess, and one more similarity striking in my mind is that they can form ionic compounds as well as they can form the covalent compounds. Like first I am telling you that how the halogens form an ionic as well as covalent compound. So you know that NaCl, so in NaCl, Na is positive and Cl is negative, they are just united to form a crystal lattice. So that means this compound is ionic in nature, right. Similarly we have CCl4, non-metal, that means a covalent compound. So similarly what to do, like we have NaH, sodium hydride, again a ionic compound, and we have hydrogen as CH4, non-metal, again a covalent compound. So that means, so this justifies the fourth property as well, that means there are 4 similarities with the halogens as well. So that means the hydrogen resembles the first alkali metal group and as well as the 17 halogen group. But to avoid the confusion, or you can say just to make the periodic table easy, hydrogen cannot be placed simultaneously. We know that we cannot place simultaneously an element in 2 groups. So that is why it has been assigned a separate position, that is why it is the first element of the periodic table, right. I think the position of hydrogen is justified now, and the similarities of hydrogen with alkali metals and halogen as well is justified, and you know that what the similarities they have, and I have also shown you with the example. So just don't forget it, right. So the second topic what we will be taking up is we now know you can say we know the introduction, where do we found, we know who gave the name, who synthesized the hydrogen, we know that what is the position in the periodic table, we know that, and what is the similarity with the halogens and the first group, we know that, and the last one, you can say almost we know that what is the importance for it and all, we are just familiar with it, right. So the next topic what we will be going to start today will be a preparation of hydrogen, that how or what are the different methods by which the hydrogen can be prepared, right. So the first we are taking, actually we have three types of preparation, right. One is the general preparation, other is the lab preparation, the third one is the industrial preparation. So by these three different methods we can prepare hydrogen, right. So first is the general preparation, means the various means by which we can get the hydrogen may have the you can say certain drawbacks or limitation that we are not using those general methods, out of them only few we are using, or there are some limitations which are just shown by those methods, but still we get to have hydrogen in that case. That means the hydrogen is produced as a result of the reactions. So first I am taking into the consideration the general preparation. So the first general preparation we have is reaction of metals with water. No matter, it can be cold, it can be boiling water, or it can be steam, but somehow after these reactions we get to have hydrogen. But there are few limitations, as I told you, that we are not using that method as a main method, but still we get to have the hydrogen at the end of the reaction, right. The second general preparation we have is reaction of metals with dilute acids. This we will be discussing what dilute acids to be used and what dilute acid not to be used, or which metal is to be used or which metal can't be used, right. So likewise we have the third more method, that is the reaction of metal with bases. I think you are familiar with the bases like sodium hydroxide, potassium hydroxide, magnesium hydroxide, all those compounds which have the hydroxide ion in them, they act as bases, right. And you know that the bases which are soluble in water act as an alkali also. So alkali is a co-branch of the base as well. All the alkalis are bases, but all the bases are not alkalis, because all the bases are not soluble in the water, right. So that is beyond our scope, because in this we won't be needing it. So just starting with the first method, that is the general preparation, and I have told you that the first method which we use is the reaction of metals with the water, right. So we have certain metals. So the first property is that the reaction of metals with water to form H2, right. That the basic method that why we are studying it is that we will be saying that whether we get H2 or not, right. So I am just taking a random example of metals, then we will be listing them in the reactivity series, and that will help you in learn in a better way, right. So the example which is striking in my mind, what I am taking for a metal is that the potassium. So what happens when I react potassium with water? We know that when metal react with water, it forms the typical bases, the strong bases. So likewise the potassium do, it reacts with cold water, no heating is required in this case, right. So when K, we know that H2O can be written like this also, do not like this H, write this H and OH in case of the place of the H2O, just remind in mind, because it will help you in making the chemical formulas, right. So it is just needed to just make you understand that yes, with what the K has to be crossed with, right. So we know that the valency of the K is this, so obviously the positive is going to attach with the negative ion. So that means it is going to form potassium hydroxide, and along with that hydrogen is liberated as H2. So this is potassium hydroxide, and this is the product which we were looking for, that is the hydrogen. But what is the actual nature of this reaction? The nature of this reaction is that this potassium react with water, you can say has a great affinity for water, and it reacts explosively. right? That means the reaction is so exothermic, that means so much amount of heat is liberated which leads to the explosion. That means the hydrogen which is liberated catches fire. So that means it cannot serve as a better method for the preparation of H2, right? Because we need an H2, we don't need that the hydrogen should burn in air or forming a certain kind of, producing a certain kind of flame or something like that. We just need a pure hydrogen. So that means obviously it is not going to be a fit method to prepare hydrogen, but still it is one of the general method by which we can prepare it, right? I am just stating few more examples for you. Similarly, I am taking an example of sodium. So when sodium reacts with water, again it is going to form its hydroxide with H2. This reaction is also exothermic and explosive, but you can say it's not too violent. It's not too violent like the first one, the potassium, because sodium is less reactive than the potassium. So obviously the heat evolved is going to be less as compared to the potassium, right? But you know what, you can say what is the limitation? One more problem is faced in this reaction. What is that? Just listen to me carefully. In this reaction, obviously the reaction is violent and explosive and explosion, everything is there, and moreover along with that, sodium starts forming or you can say sodium just melt into a globule and just darts into the water. Then what happens? So it just do not, that means you can say the collection of the hydrogen gas becomes very difficult in that case. So to avoid that, what we do, we just use sodium wrapped in something, and so that the hydrogen, it does not dart in the water and hydrogen can be collected easily. But still it is not a good method to, because again it is an exothermic and can be a violent method, right? So similarly I am taking up the example of any other metal, that is the calcium. So again calcium reacts with water to form calcium hydroxide. You know where this 2 has come? It is just because of the valency of calcium is 2 positive. Earlier I was taking the 1 positive valency elements and the calcium is 2. So obviously it will, when we will crisscross like Ca2 positive and OH negative, you know that how to make, we have just discussed in the language of chemistry as well. So this is the calcium hydroxide, and again with it we are getting hydrogen. So what is the outcome for this reaction? So obviously this reaction can act as a method of producing H2 because it is not too violent, not much heat is liberated. But the limitation comes here in another way, because the calcium is too expensive. So that means this reaction carried out for the production of hydrogen is going to be expensive. So that means, because we look for a reaction in which turns out to be cheap also, because we don't have to prepare hydrogen only once, right? We will be preparing hydrogen in a large amount. So we need a reaction which comes out to be cheap as well, and moreover it should not be violent or should not lead to any kind of explosions, right? So that means again the calcium reacts with these, all sodium, potassium, calcium react with cold water, but still it is of no use, because in the potassium it catches fire, again it's violent, and in this case the calcium is expensive. So that means these metals do not serve as a better method for preparing the hydrogen. So we have few more metals which we can list for them, like magnesium. Magnesium reacts with water, but it do not react with cold water. Keep in mind, the cold water reactions are only till potassium, sodium and calcium, right? Magnesium onward, the reaction with water is like decreasing somehow, the affinity is decreasing somehow. Like the magnesium, if we want magnesium to react with water, we need a boiling water. And when we react metals with otherwise when we react any element with water, it is going to form a hydroxide. Keep in mind, right? The reaction of any element with water is just going to result in the formation of hydroxide. But when we are using the boiling water or steam, so instead of forming the hydroxide, they form the oxides, right? So keep in mind, this is very important, and many of you just write the hydroxide. So it's not like that. Whenever an element react with the boiling water or the steam, they do not form hydroxides. They form hydrogen, but they don't form hydroxide. Instead of hydroxide, they form the oxides. So similarly, it will form the magnesium oxide and H2. So that means this reaction is the good one, because only the limitation is that we need to boil it. So that's not a big deal, right? So it can serve as a good reaction, or you can say it can serve as a good method for preparing the hydrogen, right? So similarly, I am looking up the metals whose reactivities are less than it, like aluminium, iron and zinc. they definitely react with water, but when they react and in which form they react. So they react with steam. They do not react with boiling water or hot water, they react when they are red hot. So their reaction is with typical with steam. Not in any case they react with cold water or hot water, they always react with steam. And whenever I have told you, when they react with boiling water and steam, they just form oxides, not hydroxides. So just look at the board, I am forming the oxides of aluminium along with hydrogen, iron oxide, again hydrogen, zinc oxide, again hydrogen. You need to remember that instead of Fe2O3, we get Fe3O4. That means the oxide which is stable, or you can say the oxide which is formed when iron reacts with steam, is not the Fe2O3, it is the Fe3O4. This is the major mistake what you all do. So just keep in mind, it is not Fe2O3, it is Fe3O4, right? That means the ferric oxide. So I have just told you the many examples, and below zinc we have the very less reactive elements, metals you can say, which do not react with water, right. So lead onwards, no metal react with the water. So that means if I want to just put them or list them into the reactivity series according to the reaction, so I am just putting it, just have a look. Then copper, mercury, silver, gold and platinum. You know that potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, and then copper, mercury, silver, gold, platinum, right. So we know that you can cite from the few examples what I have given you. Three of them react with water, with cold water, the reaction being violent, less violent, but the calcium is expensive. And when we talk about the magnesium, it reacts with boiling water, forming its oxide, right. And aluminium, zinc and iron, they react with steam. And when they react with steam, they form their respective oxides. And I told you, you need to remember that iron, instead of forming the ferrous oxide, it forms the ferric oxide. Keep in mind, I am repeating this again and again because this is the major mistake what you all do. You just remember that yes, you have to form the oxide, but instead of forming the ferric oxide, you all form ferrous oxide, and that is wrong. So you have to form the ferric oxide, right. Along with this we get to H2. So from tin and lead onwards, you can say the reactivity just decreases, they don't react with water, and the elements, the metals which are placed below hydrogen do not react with water at any condition, right. So that means the normal temperature, that means I am talking about the condition which is necessary, or the condition which is suitable, or the condition which we can use to at the certain condition which is needed for the production of hydrogen. So they don't react with the water in that case. So this is just I have summed up for you on the basis of reactivity series, and I think it is clear from the examples also that I have stated for you. So this is the first method what we were discussing, that is the general preparation of metals when they react with water. Now we will be taking up the second the general preparation, that is the reaction of metals with the dilute acids. So the reaction is going to happen in the same way like they were displacing the hydrogen and just combining with the hydroxide in that case. So similarly in this also they will be combining with the, you can say the radicals or the chlorides, fluorides, bromides, leaving hydrogen aside. That means they will lead to the formation of hydrogen as well. So that I am stating with an example. So second reaction, general preparation, what we are studying is reaction of metal with dilute acids. So first of all, you should know what kind of dilute acids to be used, right. So we generally use, you know the term dilute acid. Dilute acid is that, first of all you should know what an acid is. Acid is that substance which when added in water just produce hydrogen ions, right. Now if I am talking that the acid used is the dilute acid, that means that acid has more content of water in it, right. So you need to use the acid, and which one which has the more amount of water content. So which dilute acid, because we get many dilute acids, so which dilute acid you are going to use is normally the hydrochloric acid and the sulfuric acid. one question is just coming in my mind, I can't stop myself from telling you, because that is an important question. In this case, we use dilute acid HCl and H2SO4. Don't ever use HNO3, right? Because the reason being, HNO3 is strong, powerful oxidizing agent. So what does it do? It just oxidizes the hydrogen produced into H2O. So we get H2O instead of H2. Again, I am repeating for you, do not use HNO3 as dilute acid for the preparation of hydrogen from metals, because HNO3 acts as the oxidizing agent. It just oxidizes H2 to H2O. So instead of H2 hydrogen gas, we get the water. So that means HNO3 is not used, right? And I'll be stating you with the examples as well. So when we talk about the reactivity series like the potassium, sodium and calcium, they do react with dilute acids. I'm just showing you. They react with dilute acids, they just crisscross, you know that, na? How to do that? K with Cl, liberating H2. Again, if I take H2SO4 in this case, then Na2 sodium sulfate plus H2. You know that, I think you are familiar with the valencies, right? Because we did in the language of chemistry as well. Similarly, I am taking an example of HCl for this. You know this, right? You know how to do these reactions. So when they are reacting with it, so what we get to see, so obviously the hydrogen gas is liberated, but these reactions are not used, or you can say these metals are not used for preparing the hydrogen from dilute acid. Now the question must be arising in your mind that what is the reason behind when they are reacting so you can say comfortably with the acids, but then what is the reason behind? The reason behind is very important, because we need hydrogen, we don't need an explosion, right? So these all reactions are exothermic reactions. They produce heat, and they produce heat in such an amount that explosion occurs. So we don't need an explosion, we just need an hydrogen gas. So that is why these metals are not considered as right elements to react with dilute acid to produce H2 gas, right? So instead of them, we use the magnesium, aluminium, zinc we can use. Right, so I'm just because the reaction as the reactivity decreases, the liberation of heat also decreases. So somehow the small amount of heat is released, but the reaction is not violent or will not lead to any kind of explosion. So here I am writing an example. See, Mg with HCl. Again I am writing the valencies. You know, positive part is crisscrossed with the negative one. We did in language of chemistry, magnesium chloride, and then we get our desired product for which we were doing it, that is the hydrogen gas. Similarly, I am doing it with the sulfuric acid as well, because you should know that how it reacts with the sulfuric acid, because either of the acid can be used. Again I am putting the valencies. Don't put this valency on the chemical reactions. I am just putting it to make you familiar that how we are getting the compound CaOH whole twice, from where that 2, 3, 4 is coming, right? So just keep this valency in mind, or you can write in rough. So just make the desired product and directly write it here, right? So again, positive part is going to react with the negative part. So what do we get after crisscrossing? Al2SO4, it is a radical, so it has to be enclosed in bracket, 3 plus H2. So again, it is our desired product. So that means we can get the hydrogen on reacting the metal with dilute acids, but these metals are obviously not going to be used. We will be using the different metals, and moreover the lead is not used. The lead metal is not used. So keep in mind, we are not using HNO3, and moreover which metal we are not using? These three metals, because they lead to explosion, and the other one is lead, right? Now the question must be arising in your mind that lead is not a reactive element. As we are moving down, reactivity is decreasing, right? So when we react lead with the acid, what happens? Why it do not react with the